Let's continue section 10.3, polar coordinates, with a discussion on symmetry. So symmetry part A. If a polar equation is unchanged when theta is replaced by negative theta, the curve is symmetric about the polar axis. For an example of this, you may look at figure 14a. Symmetry across the polar axis means that once we've drawn the graph, the top, everything above the polar axis, is reflected below the polar axis. So we have mirror image about x. For example, the four-leafed rose that we did in example 8 would be another example of something that is symmetric about the polar axis. B. If the equation is unchanged when r is replaced by negative r, or equivalently when theta is replaced by theta plus pi, the curve is symmetric about the pole. So this is the equivalent idea of odd symmetry, where you can pick up your graph, you can rotate it 180 degrees, put it back down, and it remains unchanged. To see an example of a polar equation like this, you can take a look at figure 14b. Also, our four-leafed rose would be another example of this. If we picked it up, rotated 180 degrees, it would remain unchanged. C. If the equation is unchanged when theta is replaced by pi minus theta, the curve is symmetric about the vertical line theta equals pi over 2. So here we want to talk about symmetry across the y-axis. So one side of the y-axis is mirror imaged on the other. You can take a look at 14c, or you can think of the cardioid we graphed in example 7. Let's continue to a discussion of tangents to polar curves. So to find a tangent line to a polar curve r equals f of theta, we regard theta as a parameter and write its parametric equations as x equals r cosine theta, which is equal to f of theta cosine theta, y equals r sine theta, which would equal f of theta sine theta when replacing r by f of theta. Then dy dx is defined as it was in section 10.2 as dy d theta divided by dx d theta. Using the product rule in the previous equations for y and x, we get that the numerator, the derivative of y with respect to theta, would be f prime of theta times sine theta plus r cosine theta, where we could absolutely replace r by f of theta. Then dx d theta is f prime of theta cosine theta minus r sine theta, or minus f of theta sine theta. We will have horizontal tangents occurring at points where dy d theta is equal to 0, provided dx d theta is not equal to 0. Vertical tangents will occur at points where dx d theta is equal to 0, provided the numerator dy d theta is not 0. So let's finish section 10.3 with example 9. Part A. For the cardioid, r equals 1 plus sine theta of example 7. Find the slope of the tangent line when theta is equal to pi over 3. So first thing we would want to do is we would actually want to find an expression for the derivative of y with respect to x. So recall that this is dy d theta over dx d theta, which is equal to f prime of theta times sine theta plus r cosine theta divided by f prime of theta cosine theta minus r sine theta. So remember that f of theta is equal to r. That is, my pen is not working, guys. So f of theta is equal to 1 plus sine theta, which means that f prime of theta is equal to the derivative of sine theta, which is cosine theta, or the derivative of 1 plus sine theta, which is cosine theta. So let's replace f prime of theta and r throughout our equation. So f prime of theta becomes cosine theta. So the numerator becomes cosine theta times sine theta minus the quantity 1 plus sine theta times cosine theta. The denominator becomes cosine squared theta minus the quantity 1 plus sine theta times sine theta. Let's distribute and simplify as much as we can. So we will have in the numerator cosine theta sine theta minus cosine theta minus cosine theta sine theta. The denominator will become cosine squared theta minus sine theta minus sine squared theta. The numerator will be equal to, I think I miscarried a sign. Oh yes, so notice in our original equation our numerator had a positive sign in between our two terms. Let's correct that real quick. That means everything in the numerator is positive. So factoring out cosine, the numerator can become cosine theta times the quantity 1 plus 2 sine theta. Combining cosine squared theta and minus sine squared theta, I get cosine squared theta minus sine squared theta is equal to, alternatively, 1 minus 2 sine squared theta. So I'm going to replace that difference with 1 minus 2 sine squared theta, and then we still have a minus sine theta in the denominator. And that was using my double angle identities for cosine. So now, if I factor my denominator, my numerator will remain unchanged for now, cosine theta times the quantity 1 plus 2 sine theta. Factoring the denominator, I get the quantity 1 plus sine theta times the quantity 1 minus 2 sine theta. Then I want to evaluate this at pi over 3. So evaluate theta equals pi over 3. I will let you try that on your own. You should get -1 for your final answer when it is fully simplified. B. Find the points on the cardioid where the tangent line is horizontal or vertical. So now what we want to do is we want to take our numerator, we want to set it equal to 0, and we want to set our denominator equal to 0. So let's set each of dy d theta and dx d theta equal to 0. So the numerator was cosine theta times the quantity 1 plus 2 sine theta. We set that equal to 0. The denominator was the quantity 1 plus sine theta times the quantity 1 minus 2 sine theta. We set that equal to 0. Now set each part equal to 0 and solve. So if we have cosine theta equal to 0, the solutions to this would be theta equals pi over 2, 3 pi over 2. And I'm going to stop with just those two solutions because anything else would be an equivalent value of theta. Then with 1 plus 2 sine theta equaling 0, we would have actually sine theta equals minus 1/2. Sine theta is equal to -1/2 in the third and fourth quadrants at theta equals 7 pi over 6 and 11 pi over 6. Then for the denominator, if we set 1 plus sine theta equal to 0, we get sine theta equals -1. This is true only when theta equals 3 pi over 2. Then if we set 1 minus 2 sine theta equal to 0, we get sine theta equals positive 1/2 this time. And that would be for theta values pi over 6 and 5 pi over 6. Oops, sorry. Okay. So we know that immediately we have horizontal tangents. When theta equals pi over 2, 7 pi over 6, and 11 pi over 6. Notice I didn't include 3 pi over 2 because it's in both sets, the numerator and denominator. We also have vertical tangents. When theta equals pi over 6 and 5 pi over 6. Now, when theta is equal to 3 pi over 2, this is going to be a special case. We're going to evaluate this using limits. So let's take the limit as theta approaches 3 pi over 2 from the left of our derivative dy dx. So we already know that when I plug 3 pi over 2 into dy dx, I'm going to get 0 over 0 because 3 pi over 2 was a solution for both the numerator and denominator. So what I'm going to do is I'm going to separate my limit into a product of 2. This only works if both of these limits are going to exist. So I'm going to take the limit as theta approaches 3 pi over 2 from the left of 1 plus 2 sine theta over 1 minus 2 sine theta times the limit as theta approaches pi over 2 from the left of cosine theta over 1 plus sine theta. So I separated my fraction into a product of 2. So now I notice that when theta is approaching 3 pi over 2 from the left, the first limit would be defined. So we would have, for this guy, this first one, the limit as theta approaches 3 pi over 2 from the left of 1 plus 2 sine theta over the quantity 1 minus 2 sine theta. I would get a negative 1 over positive 3. For the second limit, I notice this is the one that causes the 0 over 0. So we need to apply L'Hopital's rule to it. So we'll take the derivative of both the numerator and the denominator. So the derivative of the numerator would be minus sine theta. Derivative of the denominator would be cosine theta. Now if I plug in 3 pi over 2 from the left, this is actually minus tangent theta. So if I approach 3 pi over 2 from the left of negative tangent theta, we'll factor out the negative to make it a positive 1/3. So we have 1/3 the limit as theta approaches 3 pi over 2 from the left of tangent theta. This would be infinite. Similarly, you can show that the limit as theta approaches 3 pi over 2 from the right of dy dx will equal negative infinity. Therefore, we have a vertical tangent at 3 pi over 2.